Sampling distribution. You better know this one by now. It is about the sample, and it's a distribution. A distribution means that it tells us the shape or spread of the data or group, and this tells us that it is a sampling measurement, which at this point in your life, hopefully you know that the name of this course, Statistics, is about sample measurement. So a sampling distribution is a distribution showing the distribution of sample statistics of a particular size, all sample statistics of a particular size sample. The shape of a sampling distribution is, for means, so X bar is a sample mean, and for some sample size n, the shape of the sampling distribution is, hopefully you guessed it and just said it out loud and everyone else in the library is staring at you now, it is normal. The center of this distribution is at the population mean, and the standard deviation of this distribution is related to the population mean. The standard deviation of this distribution is the same as the population standard deviation divided by square root of the sample size. And because the sample size is a large positive number, or a positive number of any size, square root of it would be a large positive number. Standard deviation divided by a large positive number makes the number smaller. So one thing we learned is that the standard deviation of the sampling distribution is smaller than the population it came from. One way we write this is that it is normal with center mu, the same as the population, and standard deviation sigma over root n. And the important theorem that tells us this is the central limit theorem. If you're really looking for a good time, search the central limit theorem online. I'm sure there are lots of interesting articles about what it is, how it's used. You may even find a proof of it, which can be a good time as well. Next thing is the purpose of inferential statistics. Inferential statistics is the process of trying to understand a population from a sample. So you take a sample, take some sample measurements like the sample mean, standard deviation, or don't forget p-party hat, and from those try and come to some conclusions about the population that this data came from, and make some conclusions about maybe the population mean, population standard deviation, or population proportion. That process of making conclusions or drawing conclusions about the population from a sample is what's called inferential statistics. This is another good place to practice putting that in your own words, describing that process there. Alright, the next thing I want to talk about is step-by-step method for computing each of the following. In my words, for a confidence interval, find the formula. Now remember that you need to get the appropriate one, so you need to decide whether it's a single sample mean, population proportion, decide whether you know the sample standard deviation or not, but find the formula. And then the next thing is find Z or T from the table based on the percent confidence that you want to get. So you go to your table, look for the percent confidence that you want, and then go ahead and look that value up. And just as an example, if I were using this table here, the confidence levels here at the top, if I wanted an 80% confidence and I was using a Z, I would come down here to the bottom and use a 1.282 in that formula. And if it was a t, then I would just need to know the degrees of freedom, go to the appropriate row, and then go to the column for that. Either one works fairly similar. Hypothesis test is, well, you should know this one. The sort of 4 steps: state the claims. These are the hypotheses. The alternative is what you want to prove. The null is what is already known. And that step, as you recall from the exam, one of the purposes is to help you identify what type of variables you're working with, means or proportions, and secondly, identify whether you're dealing with one or two-sided test. Second step is to calculate the test statistic. And this will require that you know what type of statistic you're dealing with. This could be a t, z, and f, or perhaps a chi-squared, depending on the type of test, and you have the formulas for those, so you'd have to calculate that. Then the third step here, we would find the p-value. You may need to know the degrees of freedom, or you may need software to do that in the case of ANOVA or chi-squared. You'd have to have that computer to get the answer there. Otherwise, for T and Z, you can just look it up. And then the fourth step is to make a conclusion. And your conclusion should be either I have significant evidence to reject the null and keep the alternative, or your conclusion will be I do not have significant evidence to reject the null, therefore I will keep the null hypothesis. Grandma's recipes, why are they so good? Well, that's an obvious one, because they're tasty. Alright, let's just go ahead and jump to these last ones, do them while we're here. The logic behind why a p-value smaller than the significance level leads us to the conclusion that we have strong evidence to keep the alternative. So if you remember, the p-value is the probability of observing a sample. Sorry for the typo, my eraser's gone, so I'm not going to fix that. For the probability of observing a sample as extreme as we have if the null were true. Alright, so what that means is that if we have a low probability, extremely unlikely probability of observing this sample if the null was true, that means that most likely the null is not true, and therefore we should keep the reject the null and keep the alternative. What we're sort of looking for, we're trying to measure here on the scale of likelihood from 0 to 1, 0 being unlikely, all the way up through likely here at 1. We're trying to decide how unlikely our evidence is. Now here in the middle is, not exactly in the middle, but is our significance level, often 0.05, not always, but it can be. And what we're using this as the cutoff to decide what's likely over here, or at least somewhat likely, versus what's extremely unlikely. So all the values smaller than your significance level of 0.05 are said to be extremely unlikely. And if it's extremely unlikely to get this p-value, that means that it's extremely unlikely of observing your sample as extreme as you have if the null were true, then we go ahead and conclude that the alternative must be true. So if the p-value is less than alpha, then we go ahead and say it is significant evidence, and we reject the null and keep the alternative. And there are different ways of saying that. I will let you look those up on your own. And on the other hand, if the p-value is greater than the significance level, then we say it is not significant evidence. And you should keep the null. Alright, last question here. This one's a reading question. Identify what statistical tool, confidence interval, or hypothesis test, and the type of tool would be used to answer each of the following. So the first question, researchers are studying weight gain, and there are two different groups of cattle. One group was treated with antibiotics, the other was not. The group treated with antibiotics had a mean weight gain of 21.3 with standard deviation 8.1. And the second group had a mean weight gain of 15.4, standard deviation of 4.5. And we are asked, is this significant evidence that antibiotics causes, or antibiotics increase weight gain in cattle? Should be a question mark. Because it's asking for significant evidence, we are going to use a hypothesis test. There are two separate sample means, so it is for two independent sample means. And they are independent because there's no relationship between the two groups of 25. It is not a matched pairs. Right, the second one, suppose a clothing company is trying to design custom one-size-fits-all Point Loma Snuggies, and they need to know how tall to make them. They would like to determine the mean height of all PLNU students, and they know that the mean standard deviation for PLN students is 2.4. They do not know the mean height. That's strange, but whatever. They collected a sample of 40 and found the mean to be 67.9. So we are dealing with means again. We know sigma. There is only one sample, so it's a one sample with means. And then we need to know hypothesis test or confidence interval. Now we're asked to predict the true mean, and we know that confidence intervals are for predicting, so it's a confidence interval. And this is for one sample means. And sigma, the sample standard deviation, is known, and that tells us that we want to use a z-test. You may want to confirm that just with your recipes, your sheet of recipes, confirm that's the right thing. Alright, last one. Researchers are trying to determine how much sleep improves student performance on exams. They have found the general population of students has a mean exam of 78.2. Researchers have 40 students sleep 2 hours the night before an exam, and let's look this up, and record their mean test score of 81.3 with a standard deviation of 12.5. Is this significant evidence that sleep increases performance on statistics exams? Because it asks for significant evidence, we know it's a hypothesis test. We saw that it was about means, and there was only one sample, so it's one sample for means. And if we look carefully, this standard deviation of 12.5 refers to the sample, so sigma is not known, and that tells us to use a t-test. The next problem, a sample of 80 PLN. Oh, by the way, I think sleep does increase performance, especially on statistics exams, so I would recommend the night before your exam sleeping at least 12 hours, if not more. Alright, back to D. A sample of 80 PLN students found that 13 had a GPA, 3.0 GPA or higher. A different sample of 86 found that 11 had a 1.0 GPA or lower. Predict. You know what, let's just throw this whole one out. I don't want to do it. It won't be on the test. It's two categorical variables, but we didn't discuss confidence intervals for those. This is a trick question. Who would do such a thing? Anyway, on to E. In a study of affluence and opportunity, middle school students were split into three groups: high income, middle income, and low income. Sample of 35 high-income students spend a mean of 5.6 hours a week on extracurricular with standard deviation of 0.8. Then there's a sample of 48 middle income and a sample of 33 low income. So it appears we have 3 groups and we're looking at means, and we're asked to see, is this significant evidence that income has an effect on opportunity, the amount of extracurricular activities they can do. So we're doing a hypothesis test. We're dealing with means, and we have 3 of them, so there are more than 2 means. Which would tell us that we want to do an ANOVA test. Alright, that's certainly a good set of problems to look at. If you had questions on any of these, I would either come by or go back to your notes and spend some more time in those sections. This is just meant to get you started studying. I'm sure there's plenty of other things to study, so you may want to do that. But I hope these help.